Hello, we can get started today with rotation. Today I will talk about how we describe rotation, how to quantify rotation, so description, then how to quantify it. In terms of quantification requires, just like any motion, it requires an idea of displacement. This time it will be angular displacement, and how much angle is displacing in how much time, the rate at which is rotating, rate of rotation, which is angular velocity, and angular speed. And whether this steady means no acceleration or accelerating motion. So that means this will mean angular acceleration. So these are the things we're gonna learn today, and we're gonna look at in angular acceleration a constant angular acceleration. These are all can be thought of in non-vector way, but they are vector properties in the sense that they do have direction. So something is rotating, then it can rotate one way versus rotate another way. We want to make a distinction, and so there is a direction involved. Okay, so let's see how would we describe rotation. What is rotation? So we say, what is rotation? Okay. Well, rotation, you can say that we have a finite body which is has a some shape and so some orientation in space, and that orientation in space is changing. So its orientation in space is changing. So it's a motion of change in orientation in space. Not going from place to place, not the change in coordinate, but change in orientation. So this is pretty abstract. You know, what do I mean by orientation? How do you speak quantitatively about this thing called orientation? So you've probably seen a dancer, for instance. Maybe it's facing you, and it's pivoting, so the nose is pointing towards us. Okay, so it's going to rotate this way. So if this is at one instant, the next instant the nose maybe is pointed this way, and hands pointed this way. His body has changed the orientation this way. So if it's an orientation, so he was facing this way, facing that way at say time 0, and a little bit later time it's facing that way at delta t equals to delta t. So you can see that couple of things you can notice in the dancer's rotation. Well, it's a I could tell the orientation from a point on the body. I could have used maybe shoulder. So you can say the shoulder is pointed that way, and then shoulder is pointed that way over here. So I could have used shoulder. So any part of the body I could have used as a marker to indicate the orientation at that instant. A simple example will be, say, if I want to look at his disc, is a much simpler example. So here is a pin, and I want to rotate this disc. So say this disc is rotating in this way about this thing we will call axis. So this is the line about which it is rotating. So we'll call that axis. In this situation, axis is an imaginary line that goes right through the body. So that's the axis of rotation. And you can see that over here, if I draw a line, say a line like that, it starts from axis and it's marked on the body. So I imagine I'm marking on the disc. So say this was at t equal to, this line was at t equal to 0, pointed in that direction, and then the disc rotated and this line rotated with it. Line is over here in some 1 second mark. So this angle can be used to quantify the rotation. So this angle is angle of rotation. And say the line was here and the line is here at t equals to 1 second. So angle rotation during t equal to 0 to t equals to 1 second. Okay, so this is now clearly, clearly if this was a rotation, say in 1 second, you went this way. Well, if you rotate the other way, he will be facing in another direction, right? So whether it rotates this way or rotates the other way, they take you to different places, and we need to make a distinction between them. Similarly here, it rotated this way versus if I had same disk and same disk, let's see, axis is here. So axis, but this one was rotating this way, and you had started out, the marker was the same orientation at t equal to 0. Well, this marker will be out here at t equals to 1 second. So this definitely is different than that. So you want to be able to tell the how you rotated. You might have rotated same degree, but you went in a different direction. So this, the way we distinguish quantitatively is we say, okay, we are going to use a right hand rule. So if the way I do it, there are several ways to do it, and you can look into there, a couple of other ways of doing it, and in your textbook. So I put my thumb, along axis. So I put my thumb along axis, and I then use other fingers I sweep. So that will be that. So thumb points in thumb points in the direction of axis when I sweep with other, and this is the front of my palm, front of palm. So this is one way to do it. So when I do it over here, I actually get this thing pointed down. So if it's a counterclockwise, so this is a counterclockwise. So if this happens, we say the rotation is counterclockwise. So this is a counterclockwise rotation. So this is what's happening. But this will not happen with this guy. This is going to go just in the opposite direction. So if I try to do this, actually, it's my thumb is not pointing up. So if you look at it from this direction, another way to say it is, if you look at it this direction, from this axis, you're looking down, and it's looking to you that this is rotating counterclockwise. Counterclockwise. So that's one way to tell the sense of rotation. And if you look at the same thing from the same axis, so I'm looking at the axis of, if this was the axis, looking down on this, then it will look like a clockwise sense. Right? You say, how did I pick this to be the direction to look at? Well, that's the convention. You have to pick one direction. From the direction you pick, if it looks like counterclockwise, then that direction will call positive direction. And so if you have already decided this to be the positive, then this rotation, this angle will be negative angle. So if this was a rotation by 30 degrees, and this was also a rotation by 30 degrees, then delta theta here will be 30 degrees, and delta theta here will be not 30 degrees but minus 30 degrees. Okay, so that's the way we quantify it, by putting a marker and then looking from the axis, and if it's clockwise or counterclockwise, so we can give angle. But so rotation is a rotation amount, or this angle, usually expressed in radians. Degrees is okay, but we don't normally express this, so radians. So the relationship to degree radian, as you may know, so if I go all the way around, then that's a 30-60 degrees. So if I go from here and I wear all the way back to here, something is rotating, so this is 360 degrees. But there's also 2 pi radians. So that's a conversion, so that will mean 1 radian is 360 over 2 pi, 180 degrees over pi. So, or you can say, how about 1 degree? 1 degree is basically divided by this. So pi over 180 radian. So these are 2 conversions you will need. The way I remember is, I just say pi radian is 180 degrees. Pi is 3.14159, etc. It goes on forever. And if you assume this is like a 3 or something, then you can see that approximately 1 radian is approximately 60 degrees. Okay, so this is how we quantify amount of rotation and the direction of the rotation. Another thing we should note is that when we rotate, we can go many turns, and this will keep coming back to itself. So the number of degrees that you're going to rotate, you're going to write down is not the last just degree from beginning to the end, but how many times you rotated. Let me draw it out for you. So say I have this, and this is my indicator, and then I rotate it for 3 seconds, and this is t equal to 0, and this keeps going, and then it went around once, came back to this place, and then another time around came back to this place, and then it ended up over here. Well, how much angle it is rotated? So delta theta will be, I had 2 full rotation, and let's say this was 30 degrees, something like that. Okay, 2 full rotations plus 30 degrees in delta t equals to 3 seconds. That's what I did. Well, so this one has to be written as one angle. So 2 full rotations is 2 times 2 pi radian, and 30 degrees is pi over 6 radian. So you can see 25 over 6 pi radian. Another way to write these angles is so-called number of revolutions. Number of revolutions. So this situation will have delta theta is 2 revolution plus 30 degrees. Well, 1 revolution has 360 degrees. So this I can convert into number of revolution. That will be 2 revolution plus 30 over 360 degrees. 30 over 360 degrees is revolution. So this is going to be 1 over 12. So 2 plus 1 over 12 revolution. So this is 25 over 12 revolution. So that's another way people write it. Okay, that brings us that a concept of speed or average speed, average angular speed. We are going to talk about that next, starting from this place, and then we're going to take it from there to angular velocity. We can talk about the vector properties later, and angular acceleration, and then we'll do some problems after that. So I'm going to stop here.